Good afternoon and welcome to today's Safer-Sim webinar. Thank you for joining us today. Before we get started, I would like to point out the chat box in your Adobe Connect window. Please use this chat box for any questions or comments. There will be time at the end of the presentation for questions and discussion, so we will address any questions or comments at that time. Now I'm pleased to welcome our presenter from the University of Massachusetts-Amherst, Aamani.
Welcome everyone for today's presentation on driver behavior and performance on in-vehicle display-based speed compliance. So I'm going to begin with a little of introduction, followed by an overview of the problem statement and a little of background and a series of methodology which involves how the scenarios were developed and how the data was collected and method of analysis and result extraction, and conclude with some research contribution. To start with, as we all know, like road signs play a vital role in delivering safety critical information to the driver, and millions of dollars are being spent in operation cost of TCDS. With advancement of vehicle-to-vehicle interaction and vehicle-to-infrastructure interaction, and OpenCV and deep learning booming. This leads us to a question: if we are delivering safety critical information to the driver in an efficient way without distracting him from performing driving related activities. So before the technology like autopilot or self-driving cars can take over completely, there is going to be a gradual transition. So this is where communication with in-vehicle display and human driver plays a major role. Traffic control devices is like a huge pool of devices. Here we're going to narrow it down to just speeding for the following reasons right here. And since the major reason why we are narrowing it down to one traffic control sign is because different information requires a different time to process. Hence, it's very important to study each each kind of devices and each kind of device and how it is being delivered to the road user. As we see from here, like more than a quarter of traffic fatalities are accounted due to speeding, as per 2017 NHTSA, and 86% of speeding related fatalities occur on non-interstate roadway. This problem statement also contributes to our scenario characteristics. Moving on, to proceed further, it's very important to understand the human error was identified to cause 94% of the crashes, and the classification of human error here can be related to speeding very well, like fail to notice speed post or a speedometer, or say lack of legibility, and traffic sign vandalism. And like as I mentioned, since the processing time and the response rate varies for different information, it's very important to understand how each information is being delivered to the road user. There are two kinds of in-vehicle displays. One is like heads-down display, and the other is the heads-up display. Heads-down display. Heads-down display falls in the region of a near peripheral region with an approximate eccentricity of 23 degrees. That's a region where the speedometer lies. And heads-up display is a macular vision region, which where the information will be displayed right on the windshield. Now that we understand that there are two kinds of displays, we also need to understand how the human vision and the different parts of human vision, so that we can take advantage of pros and cons of human vision. In earlier research work stated that central visual field was the only visual field of input that is being processed, but later showcased that the role of peripheral vision in driving environment. Human vision has two types of photoreceptors, rods and cones, where rods are like light sensitive than cones, and they detect motion, and they're non-sensitive to color, and these rods are predominant in peripheral vision. So hence we're going to make so our study also focuses on this area, where they are going to use motion and see if the information is being delivered to the road user efficiently, rather than overloading the central field that has additive detrimental effect on performance over all eccentricities. Current in-vehicle displays in practice, something, these are a few examples, as you see, like Tesla Model S and the BMW Series 7 and Volvo XC60 has their own form of displaying this information. But the question comes, are these information overloading the driver in their driving environment, or are they being delivered efficiently? Yeah. So in the methodology, like we just came across a few literature and the background, and following this will be experimental design that outlines the independent and dependent variables. Once the experimental design was finalized, it was sent to IRB protocol for approval. On being approved, scenario development phase began. In this phase, I'm going to discuss about two topics, where how the virtual world was developed, and how the in-vehicle display was developed as well. And the next phase is the data collection phase, where where participants were recruited, and the data was collected, and then is the analysis phase. Moving on, under experimental design, the major task in this portion is to identify the independent variables and the dependent variables. Here, the two major independent variables are alert location and alert style. Here in our study, alert refers to a speed alert. So alert location has two levels, virtual dash and central stack, while post mounted being like a traditional control scenario, just like a speed post on the roadside, delivering speed information to the road user. And alert style again has like two different levels, that is steady and flashing at a rate of like 2 hertz, based on the literature review. And then with these two independent variables and the control scenario, all provide a combination of scenarios. They sum up to like 5 scenarios, like a combination of virtual dash and a flashing scenario, virtual dash and a steady scenario, and similar with the center stack. Here, so continuing on driving scenarios, like mentioned, a combination of independent variables were laid out, and they sum up to give us like 5 scenarios, which includes the control scenario, that is the post-mounted or the traditional post-mounted sign scenario. So the whole experiment was performed in Arabella Human Performance Laboratory at UMass Amherst. It was performed on a high fidelity full cab simulator to gain ultimate research simulation driving experience. And it also uses like 5 projectors and provides a 330 degree field of view along with the audio channel system. In addition to the full cab simulator, we also made use of the eye tracker that records the eyeball movement, and the output is in a video format, as you see on the leftmost image. That has a crosshair that refers to the movement of the eyeball. Moving on. So the next step is development of the scenarios. Here we have 2 parts: developing the virtual world and development of in-vehicle display. So the characteristics that the study is limited to is that so the network is going to be an urban roadway, non-freeway network, as we saw in the problem statement. Where this network where the driver will experience, will come across pet crossing and stop control intersections, things like that. And the whole drive length is of about 2 miles in drive length, and with a medium density traffic in daylight driving environment. Next part is in-vehicle display. As in the independent variable alert style, we have like two levels. One is a steady level and a flashing level. So the same was developed at the speed at the virtual dash and center stack, where the flashing scenarios had a flashing rate of 2 hertz. As you see on the rightmost screen, the top image refers to a virtual dash speed alert system, and the bottom one refers to a speed alert at the center stack. So to develop this, the scenario creation was performed on a sim creator software. It's a graphic user interface which helps researchers to build and connect components, enabling power flow modeling approaches. It's a very user-friendly software. This component model also enables the user to build Altia model, which is, as you see on the left side, it's the Altia model, which interacts with the vehicle. In this experiment, it was used to design the virtual dash and the center stack of the car itself. This Altia component opens to an interactive user-friendly interface where each component can be defined to have its own properties, animation, and connections. So these 2 softwares were used to develop the scenarios for this project. So once the scenarios were developed, the next phase is the data collection phase. First we had 3 pilot runs and followed by recruitment for process. The whole experiment, the recruitment was done through advertisements, emails, and flyers, and each participant was compensated with $20 at the end of the experiment. And we recruited about like 27 participants of age ranging from 18 to 60 years, with a mean age of 27.5 years. And we also made sure we have the male-female ratio in balance, as you see on the bar chart here. So each participant underwent these 5 these five collection process, where the participant is given a consent form, and once on agreeing and signing the consent form, his eye was calibrated with the eye tracker, and he was allowed to have a test drive. Once he's confident to have five such drives, the scenarios were introduced to him one after the other in a randomized fashion, and this randomized fashion also were taken care such that the number of drives collected in each combination is not skew towards one side, as you see on the table here, where each number represents, say, like, virtual study scenario. Virtual study scenario has was the first run in five such participants. That's what this table mentions, so that the whole randomness is not skewed towards one kind of combination. The next, once the whole data was collected, like for all the 27 participants, measure analysis was performed on these six measures. The first one being like mean speed, and second one is a percentage of time spent greater than the posted speed limit, a duration of incursion or an event. And so here an incursion is defined as the time spent greater than the posted speed limit, and to the time up to which the driver drops below the speed limit. So that period is called as an incursion or an event here. And the frequency of alert zone, like how frequent these such events occur, is the fourth measure. And the fifth one is speed percentage of the speed post that goes unnoticed. This was a manual measure, a manual count using the video output. And the last one is the survey questionnaire responses. And all the first four measures were studied across gender-wise, age group-wise, and scenario-wise and order-wise. As we see, like the first measure here, the results look like that. 18 age group of 18 to 23 mean speed is significantly greater than the age group of 24 to 40. While the gender-wise analysis stated that there is no significant difference between the male and female, this actually aligns with the Ever Drive Safe Driving Report on 2018, which stated that the male and female drivers have similar driving scores. And in terms of like scenario wise, here you see the red one represents, so the whole presentation is going to have this color scheme, where the red one refers to the control scenario, and the greens refer to a virtual dash scenarios, and the blue represents center stack scenarios, and the hatch pattern here refers to flashing scenarios, and solid pattern here refers to steady state scenarios. So from this, it's very distinctly clear that a flashing scenarios, like both in center stack and in virtual dash, have significantly less speed, driving speed when compared to other scenarios. In terms of alert location and alert style, alert location, like center stack scenario was found to have a significantly less driving speed, mean speed, when compared to a virtual dash scenarios. Here, the flashing and steady state scenarios are combined to get this output result. And in terms of alert style, the flashing scenario was found to have significantly less mean speed. Similarly, same kind of analysis was performed for the second measure, where the percentage of drive time spent greater than the posted speed limit, and similar results were obtained. Here, as we see from the bar, as we see from this bar graph, the hatched one refers to the flashy scenarios, and they seem to have less mean speed compared to all other scenarios. Next comes to the frequency of events. Here it states that say in a control scenario, when a driver goes beyond the speed limit, he's just not alerted that his driving speed is greater than the speed limit, and hence he continues to drive, and hence he does not end the current event. So he spends a lot of time in one event, hence the frequency is less. Similarly, in flashing scenarios, if a driver goes beyond the speed limit, he is being alerted, and he or she drops his driving speed to below the speed limit, and this is on a very short duration, and hence there's a possibility of recurrence of this event, and hence the frequency is more for flashing scenarios. The same was studied if there's if there are any order effects, and this is significance of the fifth order that had the fifth drive of a participant had a less mean speed that was found significantly, but this significance has been distributed across all the scenarios through counterbalancing, as I had displayed in a form of a table a few slides ago. From the results from the eye tracker stated that an average of 47.73% of speed posts were noticed. In other words, like say 52% of the speed posts went unnoticed. Even though the crosshair at the speedometer resulted to overlap frequently with the alert zone, not always the response was seen in the speed behavior. This is justified by the fact that majority of the drivers don't think driving beyond 10 miles per hour is speeding. And a few results from the questionnaire is that does this alert system help you to stay within the speed limit? And 80% of them said yes, while 20% of them said maybe. Most of the participants feel the alert system helped them in some way or the other to help them stay within the speed limit. And alert type preference did not have any significance here. Some research contributions are visual cues aid drivers to maintain speed within the limits relatively significant, and it also poses the need for external means of alert cues, especially for the age group of 18 to 23, where the driving mean speed or the percentage of time spent is significantly greater when compared to the second range of age group. Flashing alert style showcase faster responsiveness in the peripheral region, and majority of the speed boost has a chance of being gone unnoticed. So this study has its own limitations, where the experiment was performed in a daylight driving environment in a low medium traffic and the nominal workload conditions. Hence, in the future work, say a cluster analysis of the speed can be performed to categorize them into incidental speeding, casual speeding, or cruising, or aggressive speeding. And a similar study can be performed to see the effect of night vision and how users respond to these alerts in a night vision environment. and in high workload conditions, and also this can be combined with auditory cues. So our project had only visual cues, and this can also be replicated in a real-time prototype automobile as well. And these are a few references, and I'm open for any questions.
So I'll give people a chance to type any questions. I will mention our next webinar will be Tuesday, November 19th. That's from the University of Central Florida. They'll speak about their research studying managed lane facilities in a connected vehicle environment. So that's Tuesday, November 19th. So here's a question. When you say the speed postings were missed, do you mean the in-vehicle icons or the roadside signs?
Oh, yeah. I meant specifically for the road sign, the post mounted road signs.
Okay. Well, thank you for the presentation, Aamani. Thank you, everyone, for joining. We will send this recording out here by the end of the week. So feel free to go back in and check that out if you think you missed any parts due to audio issues. So thanks again for coming, and we'll see you next time.